Hi everyone. Today I'll be presenting our project on modeling tennis player shot prediction using generative adversarial imitation learning. In short, GAME. Our goal was to develop a learning system that can realistically imitate professional tennis player behavior during matches. The main objective was to use deep learning to imitate individual tennis player styles. We wanted the model to predict an outgoing shot based on the opponent's incoming shot, mimicking real players. Importantly, we integrated physics constants such as ball mass, air density, gravity, and court dimensions for more accurate stimulation. And the model is the combination of generative modeling and imitation learning, and it's being fed with a custom data set created manually. uh, it's created manually from a publicly available tennis match video. Coming to the application, it can act as a coaching assistant for analyzing player shot patterns, and it's a very cost-effective alternative to Hawkeye technology. And it's very useful for style analysis, preparing players for the match, etc. Going to the next slide. Our one of the biggest gaps was the lack of public datasets that cover temporal consistent shot trajectories. We also found that many existing methods mislabeled shots or predicted unrealistic behaviors. So we decided to build and annotate our own dataset to ensure accuracy. To overcome the limitations, we build a custom data pipeline for consistent incoming and outgoing shot sequences. So here is a flowchart that replicates our pipeline here, which takes input as a video to a YOLO model, and the model detects player's position and ball's position and calculates their uh, coordinates, and then it determines the shot time, whether it's an incoming shot or an outgoing shot. And to manually annotate the shot type, we are going to rely on this condition where the distance between ball and the player is less than the threshold. We are going to pick that frame and manually annotate it to a specific shot. And we implemented a student teacher architecture using generative adversarial limitation learning, and it's a type of RIL, inverse reinforcement learning, instead of GAN based approaches, because it's very optimal method to for trajectory generation tasks. And then the flowchart here shows the heart of our model. uh, It's the Gale learning pipeline using TRPO, and here is how it works. We start by initializing the policy network and the discriminator, and we use human player data to act as expert trajectories. And here the policy generates its own trajectories by interacting with the environment. The discriminator tries to distinguish expert actions from the policy's actions, and it updates its weights using loss function mentioned here. And TRPO update rule, this is the optimization step. We update the policy using trust region policy optimization, which ensures stable learning by constraining the policy changes within a trust region using KL divergence. And this loop is going to continue until the policy successfully imitates the expert behavior. At the end, we get an optimized policy that can mimic how a real player would respond to a opponent shot. So the policy network has two fully connected layers followed by a ReLU activation, and And same for the discriminator also, that was also designed with two fully connected layers, each followed by a ReLU activation function. Next slide. Technical insights. The data set was in 2D pixel space, lacking depth, z-axis, which limits our ability to stimulate shot height. Also, because of the lack of camera calibration, we couldn't map it to the real world coordinates, but still managed to achieve strong generalization despite these limitations. Model architecture. It was implemented using TRPO to train the policy network because it ensures more stable learning by applying neural constraints on KL divergence, and it improves update efficiency. And finally, the discriminator demonstrates consistent convergence during the training. Coming to the outcomes of the model, we tested on unseen data. Our model predicted the outgoing shot with an average error of just 10 pixels. That's quite accurate given the limitations. It could even predict the shot direction, which is crucial for tactical gameplay. So here is one of the outcome where it has predicted the ball trajectory from one end of the court to the other end. Let's assume there is player 1 here and player 2 here, and player 1 is hitting uh, a shot, and the green part shows the actual trajectory, and the blue arrows here are showing the direction of the ball at every instance. And finally uh, the it achieved the final position of the ball, so it's quite accurate. Yeah, thank you for your attention. Bye.